All right, so first when we look at this chart, we see negative 70. What is negative 70? That's called our resting membrane potential. What are the things that cause resting membrane potential? So we have leak channels.
The sodium potassium pump.
We have, but that maintains it.
Okay.
What causes it? So the leak channels where potassium moves out and sodium moves in, and we have more potassium channels than we do sodium channels. So more positive charges are moving out than in. Now, if it were just potassium and we didn't look at sodium, if it were just potassium, it would actually go as low as negative 90 millivolts. And we would say that's the equilibrium for potassium. But we don't just have potassium, we have sodium moving in. So that brings up that resting membrane potential to a negative 70. More positive charges moving out, but some moving in. And in addition to that, we have negatively charged proteins. So that creates our resting membrane potential, right? So that's where we start, at negative 70.
When is sodium going out of?
What is it going out of?
Like when
So these leak channels are always open, and sodium is always moving in.
so it doesn't. Potassium is always going out.
Potassium is always going out. Sodium is always going in.
Okay.
Unless we have a pump working.
Which is at like the end of the.
And the pump will help to bring it back up to resting if it dips too low, right?
Okay.
So after all this sodium is moving in and the cell's getting full of sodium and all this potassium is moving out and we're losing all the potassium, we have to reestablish the concentration of sodium and potassium inside the cell.
To get to that resting.
To get to resting. So then the sodium potassium pump kicks in and it pumps the potassium back in and it pumps the sodium out.
And that's after the hyperpolarization, right?
And that is at the end of hyperpolarization, after all the potassium voltage gated channels are closed.
Okay.
Then the sodium potassium pump goes back in, and we'll talk about that. Okay? Monique, did you have a question? Okay. So now we are, now we're at resting, but now there's a stimulus. So we get some type of stimulus there, and the stimulus we've been talking about is acetylcholine binds. So when acetylcholine binds, that's our stimulus. Acetylcholine gets released, and it's going to bind to what channels on the dendrites? So at 1, what are we going to see? What is ACH binding to? Right, so we have chemical-gated sodium channels. And where are they found? Dendrites and cell body. All right, so they open up. So now these sodium channels, all these, we still have the leak channels open, but now all these other sodium, these chemical-gated sodium channels open. So now we have even more channels open. Sodium's going to do what? Move into the cell. So sodium moves into the cell, and it's a positive charge. So what happens to your charge? It gets more positive. Anytime we get more positive from resting, anytime we get more positive from resting, what do we call that? Depolarization. That is depolarization. Depolarization, right? So now we have these chemical-gated channels opening up. Sodium is coming into the cell, and in this short little distance, what do we call that then? What type of potential is that called? Graded potential. So that is a graded potential. Yep, anytime you get more positive than resting, it's depolarization.
More positive than resting.
More positive than resting. Anytime you're more positive than resting, it's called depolarization.
Can you just repeat the graded potential?
Actually, anytime you get more positive, when you're going to a more positive number, it's called depolarization.
The graded potential is between.
So the graded potential is,
threshold?
yep, it's
Threshold.
any time above resting, so negative 69, to anywhere below threshold, which is negative 60. So it's anywhere from negative 69 to negative 61. That is our graded potential. It has to be between those two things. It has to be below threshold, but it has to be above where the cell is at rest. Okay? So that is the start. That's what's going to start. And then if it hits that next point is what we have right there is threshold. Threshold is negative 60. So when the charge inside the axon, the initial segment of the axon, hits negative 60, what channels get activated to open? Good. It's voltage because it is sensitive to the negative 60, so it's voltage-gated sodium channels. So the voltage-gated sodium channels open, and there's a massive amount of them, right? There's a ton of them. So sodium starts pouring into the cell, and the cell rapidly depolarizes, so we call that rapid depolarization. When it rapidly depolarizes, right? And then we hit the peak here because positive 30 is another voltage that these gated channels, those voltage-gated channels are sensitive to. So at positive 30, what happens to the voltage-gated sodium channels? Yep, so voltage-gated sodium channels close. And what happens to our voltage-gated potassium channels? Voltage-gated potassium channels open. Right? So sodium stops moving in. So we're not going to get any more positive than positive 30 because all the gates are closed. Sodium can't come in. It's not going to get any more positive. The voltage-gated potassium channels open, and so potassium starts to move out. Potassium's always moving out unless it's pumped in. So it's moving out, carrying its positive charge with it. So now the charge inside the cell is losing positive charges, and it starts to become more negative, right? What do we call that? So repolarization. Repolarization occurs when potassium moves out, right? Potassium diffuses out of the cell. Then we hit negative 70 again, okay? So we're going to hit negative 70, and this is another voltage that the potassium channels are sensitive to. So at right here, about right there. So at negative 70 millivolts, those voltage-gated potassium channels, voltage-gated potassium channels start to close. But they're not all closing at once. So what does that mean to our charge? Our charge will continue to drop, get more negative until all the potassium channels are closed. All potassium closed. Okay?
That's at negative 90.
That's at negative 90, yeah, negative 90. It can go all the way down to its equilibrium, and then all the channels are closed, okay? Now, though, we see that that charge starts to come back up to resting again. So what causes it to come back to resting? Right. So this is where it comes back to resting because of the sodium-potassium exchange pump and the leak channels. Right? Those two things are going to bring it back up to resting because sodium's been flooding inside the cell. Well, now we got to get rid of the sodium. So the pump is going to pump the sodium back out. Potassium has been leaving the cell. So now we have to get more potassium back in the cell. So we have to pump it back in. Okay? but always, normally, sodium wants to come in and potassium wants to go out, always. That's what they want to do. And that's what they will do unless we pump them in the opposite direction, okay? So, right? This little bit here where we're dipping down to -90, that is called hyperpolarization. Hyperpolarization. So we had depolarization, repolarization, and hyperpolarization. All right, let's look at those. Let's go and look at these questions then. Okay, with all of this on here. Knowing what we know now, which area of the graph shows when voltage-gated sodium channels are open? 2, right? That's when the voltage-gated sodium channels are open. Which area of the graph shows when chemical-gated sodium channels are open? 1, right? That's when that ACH binds. ACH is a chemical, so ACH is stimulating that. So those gates are stimulated by chemicals. We call them chemical-gated sodium channels, right? Which area of the graph shows when voltage-gated potassium channels are open? Yep, so at 3, right up at positive 30 millivolts, that's when those potassium channels open, and they stay open all the way down until -70 when they start to close. Right? So that was 3, and 8 was 1. Okay, right there. What's occurring between 2 and 3? It's just another way to ask this, right? I just keep asking kind of the same questions, but what happens between 2 and 3? The sodium ions are entering the axon and causing depolarization, right? Okay, and then 11 is the same question, so I apologize for that. What area of the graph shows when chemical-gated channels are open? Sodium channels, that again is 1. And then the last question is, what's occurring at the area labeled number 4? So here's 4. It's hyperpolarization. What happens during hyperpolarization? Excessive potassium has diffused out, causing hyperpolarization. All right, so now we're going to go here. These are questions that are multiple choice questions without a graph. So during repolarization, so now you have to visualize that chart, visualize what's happening with the cell. What happens during repolarization? We're coming down. Potassium ions are involved. They're doing what?
Moving it.
Potassium ions are doing what?
Oh, moving out.
Potassium ions are moving out of the cell, right? We're getting more negative, so the positive charge is leaving the cell. Okay. If chemically gated sodium channels in the postsynaptic membrane were completely blocked,
A.
D.
okay, let's look at that. So this is our synaptic terminal. This is our postsynaptic cell. So this is where the neuron is releasing that acetylcholine. And acetylcholine has to bind to the receptors. It has to bind to the channels, sodium channels over here on the other side, on the postsynaptic cell, right? So they're supposed to bind there. And when they do, then sodium moves into the cell, right? Isn't that what happens with chemical-gated channels? What we're saying here is that the chemical-gated sodium channels are blocked. So does ACH still get released?
Yes.
Yes. ACH is still getting released from that presynaptic cell. Nothing stopped it.
But it's not going in.
But it's not binding, so it's not creating that synapse. That synapse is not occurring. ACH gets released, but it can't bind to the receptors, so no synapse occurs. Right? Yes.
Is there ever is C ever,
A smaller action potential would result.
Yeah.
So we have that all or none principle,
okay.
which says if you hit threshold, you're getting an action potential,
Yeah. I was
no
just
matter what.
curious if that was ever actually
Yeah.
a thing.
Yeah.
All action potentials are the same. They
Yeah.
either happen or they don't.
Yes.
It's not like a.
They're all the same size. They happen or they don't.
Okay. Yeah, 'cause there's a lot of
What triggers the release of acetylcholine from that synaptic terminal? Yeah, so when that action potential is coming down that neuron and it gets to the synaptic terminal, that causes these calcium gates to open up and calcium comes into the cell. And when calcium diffuses into the cell, that causes acetylcholine to be released. Right? So what's our answer? The diffusion of calcium into the synaptic terminal. Okay? What opens or closes in response to binding specific molecules? The key here is molecules, right? That means that it is a chemical gated channel. Not voltage. If it said specific voltages or specific millivolts, that would be voltage gated. Okay, leak channels are always open. They don't close. Which of the following is not involved in creating the resting potential of a neuron? So we went over the resting potential. Which one of these is not true? Which one doesn't cause it? Right, so the membrane permeability for sodium is greater than potassium. So what that is saying is that more positive charges are coming in than positive charges are going out. Is that what happens? No, because the inside of the cell is negative. So we have more positive charges leaving than staying in, and that creates that negative 70 millivolts, right? More potassium leaving than sodium coming in. And then the all or none principle states that all stimuli great enough to bring the membrane to threshold will produce identical action potentials. They all go up to positive 30. They can't go any higher than that because those sodium gates slam shut at positive 30. Okay? All right. Hope that helped.